Yesterday we didn't have time to finish up all of chapter 9, but today we will, and we'll do some review problems as well. The last part of chapter 9 is on oxidative cleavage, or ozonolysis. And ozonolysis is a really unique reaction. We don't really see any reactions like this in the rest of chapter 9. But I'll show you guys the brief intro of it. If we have an alkene, specifically we can think about these hydrogens coming off of the alkene, and we treat it with ozone, which is O3, and then we follow that by treating it with DMS, which is dimethyl sulfide, or zinc and water. Both of those are good at reducing the ozonide product that we get out. We can actually get a new product. And I'm going to draw it kind of funky at first. But essentially all we've done with this product is we've clipped this double bond and we've added in 2 oxygens onto it. So it's a ring opening reaction. If you notice, the carbon on each end of the alkene had a hydrogen attached. It still has a hydrogen attached. So in this case, we're forming aldehydes. We can draw this a little bit differently because I don't really like drawing molecules this way. We can draw it linearly. So let's get this on there. We've got 1, 2, 3, 4, 5, 6. You can draw it either way. Some people prefer to draw it on the left, or the left side type drawing when they're first learning. That way they remember where the double bond was. But once you get good at these, try to draw them linearly. Just make sure that you don't lose or gain an extra carbon at some point during your drawing. So ozonolysis is really useful for cutting double bonds. So it cuts double bonds and turns them into a ketone or aldehyde. Ketone or aldehyde. Whoops, forgot the L. In this case, I'm not expecting you guys to know the mechanism. The mechanism's a little convoluted and doesn't really help you with this process. Just remember that it's used for cutting double bonds. So let's do an example of an ozonolysis reaction. So we need to have an alkene in order to perform ozonolysis. So I'm going to pick this one. And this time we're going to treat it with our ozone, which is O3. And then we'll treat it with zinc and water. Ozone is typically made on site in a lab, so you have an ozone generator. It's a really cool color when you create ozone, and it's typically a light blue. So what would happen if we split this double bond? Would our product be a ketone or an aldehyde? Ketone. So let's take our pretend scissors, cut this double bond, and we know if we do this, we're going to get a ketone there and a ketone there. Are they the same or are they different? They're the same. So we just get 2 equivalents of our ketone out. So in this case, we only need to draw it once and then just write 2 equivalents, or you can draw them both out. Let's do a different one, but this time I'm only going to give you the products. So again, we've got ozone. This time we'll use DMS, or dimethyl sulfide. Let me fix this 3. And we've got a diketone now. What would our starting material have to be? And I'll give you guys a hint too by giving you the molecular formula. It'd be C10 H16. Once you think you've got it, check with your neighbor too and see if they agree. Raise your hand if you think you got this one. All right, a couple people. Give you guys another minute. Give you a hint. The product only has 5 carbons. The starting material has 10. All right, so let's take a look at the answer for this one. So if we have 2 alkenes in there, we can actually cut both of them, right? So the alkene on the left can be cut, and the alkene on the right can be cut. And again, we'd get 2 equivalents of our ketone coming out. So in this case, we're actually doing a double ozonolysis reaction. Have you guys ever handled rubber that's really old? Do you guys notice that rubber, when it's old, gets kind of brittle and you notice a lot of cracks in it? This is ozonolysis on a very practical level. Rubber has a lot of isoprene units in it, which have double bonds. And so natural rubber, over time, reacts with trace ozone in the air and will actually start to degrade, and the rubber will lose its structural integrity. This becomes a really big deal with sensitive equipment, specifically space exploration, where they have rubber O-rings in a lot of the gaskets. If those rubber O-rings get cracked or damaged during a shuttle launch, they have to immediately be replaced. And so this is called rubber cracking or rubber deterioration, and it's an example that you see of ozonolysis on a regular basis. This used to be a big problem with car tires too, or if you parked your car outside for a long time, the sidewalls of your tires would start to crack, and it would make your tires much, much weaker and more prone to blowouts. So if you watched Christmas Story this last winter, did anybody watch that?
Where the kid puts his tongue on the...
Yeah, the kid puts his tongue on the pole. The dad has this whole thing about trying to repair flats as quickly as possible. That's because blowouts used to be really common from ozonolysis problems with tires. Now we've added some new chemicals into the tires that prevent it from happening as easily. So kind of a weird example that I thought of when I was watching the Christmas Story this winter. All right, so that's pretty much it for the reactions for Chapter 9. I know Chapter 9 was pretty reaction heavy.
Yeah.
So let's take a look at our summary of reactions. This is in the back of the chapter. From here on out, what I really recommend doing is flipping to the back of the chapter and looking at the summary of reactions, and then try to make some flashcards, and then quiz yourself. Quiz yourself every night if possible. What I typically would do is I would have the starting material and a reagent, and then on the back have the answer, and then try to make sure I knew what the answer was. Or I would omit a product or a reagent, and then have the reagents on the back of the card. That way you know what reagents are necessary. Yep.
So like questions on the quiz would just be, you give us what you're starting with, your reagents, and then ask for like a product or vice versa.
Yeah, so my quizzes, if you're not familiar with the format, I'll usually have a box that's empty where I want you to draw in the product, or I'll leave the reagent box empty and ask you to fill in the reagents, or I'll have the product or the starting material box empty and give you the reagents and products and want you to predict the starting material. So kind of like we did on this ozonolysis example. And I may have 1 or 2 mechanism problems for the easier mechanisms from this chapter.
So and then at the end of chapter 9, it talks about synthesis, I think?
Yeah, we kind of covered that with our problem of the day yesterday, as long as you can do some basic synthesis. I'm not going to ask anything too in-depth at this point. I just want us to practice because later on this term and third term, we'll be doing a lot of synthesis. It's a good question. All right, so we've got this really large chart, but let's try to do a little bit of review. So I'm going to add in one more review page. Oop. and then we'll do some practice problems. So the first thing I wanted to review was Markovnikov versus anti-Markovnikov. And Markovnikov versus anti-Markovnikov comes into play with a handful of reactions that we've learned this term. So let's just draw our example alkene. And we're going to have addition of, I'm going to call it hydrogen in blue. And then some other unit, I'll call it A. And we're going to add this across double bond. We have two options. We can add in our A group there and our hydrogen there. Let's change the colors. Or we can add them in the reverse order across that double bond, and we can say, all right, let's add A on the end and our hydrogen in the center. Whoa. Which one is our Markovnikov product? The left or the right? Left. So we've got Markovnikov. I'm just going to abbreviate it. And anti-Markovnikov. Now we've got a bunch of reactions we need to think about. Is acid catalyzed hydration Markovnikov or anti-Markovnikov? That's when we react just H3O plus hydronium. It's Markovnikov. So we'll put this on this side. So acid catalyzed hydration. What about hydroboration oxidation? Is that Markovnikov or anti-Markovnikov? Anti-Markovnikov. So we've got hydro. Or in the second step, it has peroxide. Both of these methods are used to install alcohols. One's just used to install it in a different position than the other. The cousin to acid catalyzed hydration that was also talked about was oxymercuration. Demercuration. And why would we use this instead of acid catalyzed hydration? To prevent rearrangements, right? So acid catalyzed hydration, we go through a carbocation intermediate that tends to rearrange. Oxymercuration, demercuration, you avoid that rearrangement. What about if we added in hydrobromic acid and it's nice and pure? Will it be Markovnikov or anti-Markovnikov? Markovnikov. So we'll write HX, and then I'll say without peroxides. And we know if we do the same reaction with peroxides, we get our anti-Markovnikov product. So we have to pay attention to the order of addition across our double bond. Each reaction is fairly specific out of these, whether or not it adds Markovnikov or anti-Markovnikov. Now there's some stereochemistry too. Markovnikov versus anti-Markovnikov deals only with regiochemistry. Regiochemistry means which carbon is the addition occurring at. Stereochemistry means which direction is it facing. So we talked about this quite a bit with syn and anti-addition. And this deals with stereochemistry. So let's take a look at some examples of this. I'm going to draw a new double bond. And we're going to have addition of X and Y this time. So I'll do X in blue and Y in red. So we can distinguish them. And if we do this, we can have addition across that double bond. And we get two products. And we also get enantiomers of these products. And in one case, you get addition on the opposite side. And one, you get addition on the same side. So we've got Y and Y. I'll do X and X. Which one's sin, the left or the right?
Oh, the right.
The right. So in this case, we've got sin, and this one we've got anti. And we've got reactions where we can favor sin or anti as well. So let's take a few of these example reactions. What about hydrogenation? Is that sin or anti? Is there a question? Scroll down. Okay. Is hydrogenation going to be sin or anti-addition of hydrogen? Sin. So we can add this onto our sin list. So hydrogenation. So what reagents do we need for hydrogenation besides hydrogen gas?
Need a metal catalyst.
Metal catalyst, normally platinum or palladium. All right, what about if we want to do a diol, but we want it to be sin? What do we use? So X and Y are both alcohols, and we want them to be sin. So sin diol formation. Yep, osmium tetroxide. So anytime you see osmium tetroxide, you're going to get your sin diol formation. You can also use potassium permanganate, although it doesn't work as well, and oftentimes you get a lot of side reactions. What if you want your anti-diol?
Use that MC.
Yeah, MCPBA. So MCPBA. There are other reagents. Make sure you remember that it's not just MCPBA. If we only add MCPBA, what do we get? Had a special name, started with an E. Epoxide. And so after we add our MCPBA, we need to add acid and some sort of nucleophile in order for it to open up. All right, so we've got our diols. What about halogenation? If we add elemental bromine, will that be anti or sin? Anti.
For the for the anti-dihydroxylation.
Mm-hmm.
On the chart, there was another reagent they said you could use.
So let's take a look back at our chart. So if we're trying to do anti,
That number 8. Yeah.
there's another one called peroxyacetic acid that occasionally they'll use in a book. Usually it's MCPBA though.
That's MCPBA?
Yep.
Oh, okay.
So MCPBA, this is just an abbreviation for it. There are a couple other peroxy acids you can use besides MCPBA, but MCPBA is far and away the most common. That's a good question. All right, so let's go back to our concept review. Bromination, we said, would be anti. What about hydroboration oxidation? That's when we add our borane and THF. It's going to be sin. So we have to think about that hydrogen is adding to the same face as the alcohol. Oh, sorry, wrong side. I have it flipped in my notes. Thank you. Hydroboration, oxidation, and same with oxymercuration. Demercuration. And I'm going to put a little asterisk here because I want to clarify what I mean by that. Let me move this up too so everyone can see. In this case, we have to pay attention to the hydrogen that's also being added. So it's syn with respect to the hydrogen that's also added. Oftentimes you could have another alkyl group and it looks anti, but we're really comparing the addition of the hydrogen and the alcohol in these cases. So they're going to be syn to one another. All right, what about halohydrin formation, where we put in bromine and then we add water? Is that going to be syn or anti? Anti. It's very similar to bromination, but we have water out competing for the second step. So that is Br2 and water. Bromination is just Br2. So we can clarify that there's a difference there. And we get one where we get the dihalide and one where we get the halide along with an alcohol. All right, the last thing I wanted to cover was ring opening reactions, because quite a few of these do involve some sort of three-membered ring that's an important intermediate. So let's take a look at the ring opening reactions. And what I mean by that is bromonium, mercurium, or epoxide type reactions where we have some sort of three-membered ring. And I'm going to call this atom Z because we know it can be a variety. And if we have some sort of nucleophile, this nucleophile can add, and which side will it attack?
More, carbon that has more stuff going on.
Yeah, the carbon that's more substituted. So in this case, the nucleophile will add in to this side, ring open, and then we get our anti addition. But let's draw out our product that we get. So we've got our Z atom that opened up, our nucleophile that added in. I'll keep this negative, that way our charges bounce out. And then we'll have these groups flip open like that. And so in this case, that Z atom can be either mercury, bromine, or oxygen. Right? And we said that our, let me change to black, the nucleophile will always attack the backside of the more hindered carbon, or the more substituted carbon. If Z has a positive charge. This is a really important if, and we're going to talk about this a lot more when we cover epoxides again in our alcohol chapter. But for right now, just try to remember that the nucleophile, in this case, is always going to attack the more substituted carbon. Why does it do that? It's a more stable carbocation, right? So when we drew that transition state, that carbon goes through a transition state where it has a partial positive. The more substitution it has, the more stabilized that partial positive is, just like carbocation is more stabilized when it has more substituents. Yep.
The backside attack inverts the stereochemistry, right?
Yep, exactly. It's kind of like an SN2 reaction because you're doing that backside attack and flipping stereochemistry. That's a good question. Let me even add that in. Flip stereochemistry at attacked carbon. All right, so these were the key features. We have ring opening, which is also stereochemistry. We had our syn versus anti-addition. We had all of these reactions. And then we had our Markovnikov versus anti-Markovnikov. I know this is a lot of reactions. Try to practice them in small digestible chunks. I recommend working on it for like 15 minutes, then take a short break, and then come back and work on it for 15 minutes. If you sit down and try to pound through this the night before a quiz or an exam, your brain is going to hurt. Yeah? Go up.
My brain hurts when I leave this class.
Your brain hurts when you leave this class.
So you said regiochemistry is which carbon?
Yeah, which carbon does the addition take place at? Stereochemistry is what face of the carbon does the addition take place at? So remember, stereochemistry is looking at three-dimensional space. Regiochemistry is looking at constitutional isomers. All right, so it looks like we have about 20 minutes left for practice problems. So we're going to try to go through these. With these practice problems, I'm going to give you guys some time to work on them. Please don't work on them just by yourself. Work on them for a little bit by yourself, and then try to talk to the people around you. You can even move your tables around and talk to one another. But I'll throw the first set on the board. The first one is problem 950 from the book, so it's in the back of the chapter. I thought it was a really good practice problem. It's very similar to our problem of the day, but it asks you to work with a bunch of different reactions here. So try to come up with the product for A, B, C, D, and E, and then we'll get together as a class and see if we can come up with these too. Have you done all of them? You too. So with MCPBA, what sort of addition product are we going to get? Anti-diol, right? So in this case, are we going to have to be concerned about stereoisomers? Try drawing both and then see if they're identical or if they're enantiomers or if they're diastereomers or what their relationship is. You can assume with hydronium that there is water as well. So it can be a proton donor, and then the resulting byproduct is water. Yeah.
Do we have to draw?
One is red and one is...
You don't need to draw a mechanism for formation of the epoxide. But you should know how to do the reaction once it is an epoxide and it ring opens.
What, say that again?
So the formation of the epoxide, that three-membered ring with oxygen, I said you don't need to know that mechanism, but you do need to know the ring opening mechanism.
Oh, draw the ring opening?
Yeah. This one's only asking for products, but it's always good practice to draw the mechanism if you can. All right, raise your hand if you got A already. All right, let's write A down really quick just so we're all on the same page. All right, so for A, you'll get two products. They'll be enantiomers to one another. You've got one where it's OH going up. Actually, let's avoid stereochemistry there because we know it's not a stereocenter. OH. And then we've got another OH that could be a dash or a wedge along with an ethyl group. And then we've also got its enantiomer as well, right? So this would be our product for A. The reason I didn't draw stereochemistry here is it doesn't matter, right? It's not a stereocenter, so we could draw it however we want. We don't need to include dashes and wedges when it's not a stereocenter. Yep. Sorry, say that again?
Did you say that the shorts or bleed steps for that?
I said if you can draw the mechanism, great. That helps people a lot in order to get to the product. But for this problem, they just wanted the final product. You guys want to see the mechanism? Okay. All right, let's do the mechanism for this one. So with MCPBA, so you form your epoxide, right? Plus it's an enantiomer, so that could be either both dashes or both wedges. Then the next step, we've got our proton. So this positive charge, whoop, that's not positive yet, excuse me. This lone pair on the oxygen can come around and grab this proton. The oxygen was from the MCPBA. It delivered that oxygen in order to form the epoxide, which is the three-membered ring. Once we have that epoxide, we can protonate it. Let me draw this a little bit better. So now we've got our epoxide. And water is also assumed to be in solution. Which side is that water going to attack? The more hindered or less hindered? More hindered. Then it will ring open. And we've got this alcohol over here. Let me draw this a bit better. And then the last step, you'd assume that you'd have this in quite a bit of water. So this water can do the deprotonation. and we get to our final product. I just have it drawn a bit differently.
Mr. Reynolds,
Mhm.
Dr. Reynolds, I don't have my book with me. Did I have a misprint on this? I draw that, I didn't see the back.
Oh, that's right.
Just take the bond away?
Hydrogenation. You guys want me to scroll back to the main products or starting material? Yeah.
If you were to put this on the quiz, what do you want us to like show the mechanism from? Everything, or-
This would be the mechanism I would want from the quiz. So this first step with the MCPBA, I don't expect you to draw that stepwise mechanism. From here on out, those are pretty simple mechanisms.
Yeah. Cool.
All right, let's go back up to the main part. What happens if we add hydrobromic acid?
It adds to the
Yeah,
more
the more
substituted
step.
side.
Yeah, exactly. So if we look at the more substituted side of the alkene, it's going to be this side. So our final product is going to have a bromine add to the more substituted side and a hydrogen add to the other. So let's actually just draw it in place. We've got 1, 2, 3. Do we need to worry about the enantiomer? No, because there's no stereoisomers here. So pretty easy for that one. We're doing a Markovnikov addition of bromine. What about for C? What would happen?
Just breaks the bond.
Would it break the bond?
Or it takes, no, it doesn't break the bond, sorry.
What happens to the double bond?
Yeah.
It becomes a single bond, right? We know that the addition would be syn, but again, it doesn't matter. We don't have stereochemistry going on here, so it doesn't really affect us a whole lot.
Is that it for that one?
Yep, that's it for this one. Again, I don't expect you guys to know the mechanism for the hydration. It's actually surface chemistry and a little beyond the scope of this class.
So all that happens is double bond.
Yep. Hydrogenation, you take a double bond, goes straight to a single bond.
What happens to the electrons to the double bond?
What's that?
What happens to the electrons in the double bond?
They're the nucleophile. The pi bond acts as a nucleophile and grabs a proton on the surface of the palladium or platinum. Yeah. All right, what about with D? Is it going to be syn or anti? Anti. Okay. So let me actually do D over here. We've got BR, BR. Let me slide this all the way over. First step, we'll grab this bromine, kick off the bromide. Then we form our bromonium ion, which has a positive charge. Let's see, we've got 1, 2, 3.
You
1,
want
2.
us to know this mechanism, right?
Yep. So for this one, we've got Br minus floating around. This Br minus will add to the more substituted carbon, slingshot it open. The other thing, too, that's important to remember is that we get the enantiomer here. The bromine can add from either face of that double bond. And then when we do that, we've got this bromine added in from underneath. Let me draw this a little bit differently. Sorry, guys. In this case, the carbon shown in green there is not a stereocenter, so we don't have to worry about dashes or wedges, but do we have to worry about an enantiomer? Yeah, because we could have one where the bromine, instead of being a wedge, is actually a dash. So in this case, we'd have to worry about the enantiomer. So this was, if we go all the way over, this was D. Whoa, shoot. Sorry. So let's,
What if, is it okay if my bromine was just shooting up, where to go? Like, you know how you have the first one pointing down, kinda?
mm-hmm.
I had mine going up, like that.
Yeah, it doesn't matter because there's no stereochemistry at that green carbon. It's achiral.
Okay.
Yeah. Or it's not a stereocenter, I should say. All right, if we look at the next one, what's the reaction called? If we have the borane, THF, followed by peroxide and sodium hydroxide. Hydroboration oxidation. Does that add Markovnikov or anti-Markovnikov? Anti. So if we look at the double bond, it's going to add an alcohol to this side. And it doesn't really have a preference. It can occur at either face. So if we look at this one, let's actually do it down here. This was one of the ones where I said you don't need to know the mechanism. Oh, let me move this down a bit. This is BH3.THF. This is H2O2. And sodium hydroxide. If we do this, you've got a free card to skip the mechanism. But you do have to worry about the enantiomer. And this would be product E. That what was being added in? So hydroboration oxidation, you're forming an alcohol always. Yeah, so in this case, the alcohol gets added to the anti-Markovnikov side of the alkene. If we wanted to do the Markovnikov addition of an alcohol, what reagents would we use? If we wanted to add the alcohol instead of to that carbon, we wanted to add it there, the green carbon, what reagents would we use? Yeah, the oxymercuration, demercuration, or we could try to use acid catalyzed hydration and then hope it doesn't rearrange at all. In this case, acid catalyzed hydration would work because we're forming a tertiary carbocation. I wouldn't want to rearrange. Go up. All right, sorry, these notes are a little scattered. They're in your book so that you can continue working on them. Is it okay if we go back and look at the other practice problems? Thanks for the vote of confidence over there. All right, the next one is problem 971 from your book. So if you want to jot that down, you can pop open your book this weekend and finish it because we're not going to have time to go through all of these.
That was a quiz going to look like, huh? You're just going to put something in the middle and go zero.
It may not look like that, yeah.
971?
Yep, 971 from the book.
Probably. Okay.
So let's look at reaction 1 first. We're going from an alkene to a ketone. It's ozonolysis, right? It's kind of the odd duck in the chapter because it's not a typical addition reaction. But if we look at problem 1, it's going to be first ozone, and then second we're going to have like zinc and water. What about for...
Where does the carbon go that's on the end initially?
It blows off as a gas. So it actually turns into, I think, CO2, I believe. All right, for reaction 2, we're adding bromine. Is it adding to the Markovnikov side or the anti-Markovnikov side? Anti-Markovnikov side. What reagents do we need to do this transformation? Yeah, I heard somebody say peroxide and HBr. So I'll do ROOR. It doesn't really matter what peroxide it is, just as long as you've got some of it in there. What about reaction 3?
Hydroboration oxidation.
Yeah, we're adding alcohol to the anti-Markovnikov side of the alkene, so it's going to be hydroboration oxidation. This is a two-step reaction, so we've got BH3.THF for the first step. And then we've got peroxide and sodium hydroxide added in the second step. So like I mentioned before, the trick whenever you're trying to add to the anti-Markovnikov side is look for the peroxides, and remember that you need a peroxide in order to get an anti-Markovnikov addition. All right, what about reaction 4? It looks like we've got a diol, but it doesn't show any stereochemistry. Yeah, you could do MCPBA. For this one, 4, you could do MCPBA followed by acid and water. What about if we use the osmium tetroxide? Yeah, it would work as well. In this case, they don't show stereochemistry. Stereochemistry doesn't matter, because it's the same product regardless of the stereochemical outcome. So osmium tetroxide, and then a common reducing agent to get that osmium tetroxide off is N-methyl morpholine, or NMO. Just remember osmium tetroxide does the syn-diol, MCPBA would do the anti-diol. All right, let's do the last one here. We've got reaction 5. Yeah, the halohydrin reaction. What reagents do we need in order to get both halide and an alcohol installed? Do we want to use HBr? No, because then we would get just one bromine and no water added. So we've got to add Br2 and water. So for reaction 5, we need Br2 and let me just do it over here. And water. Going through problems like this is the best way to study. You just repeat and repeat and repeat. If you look in the back of your textbooks, there's quite a few problems like this. And if you need an answer key, you can come talk to me and I can either loan it to you, or you can quickly check your answers, or just check with your friends and then compare answers and then argue if you maybe are in disagreement, or pat each other on the back if you got them all the same. It's an excellent way of studying. If you have any questions, let me know. I'll be in the fishbowl tomorrow for my office hours, so I'll be done there.